Hello and welcome to this Raycastle video short. The short presentation is on IP address allocation, and we'll start by looking at IP address allocation in the current world of IPv4. So to be a member of an IP network, and I'm going to use a laptop as our starting point, which is connected to a network, a local area network such as the one in your home networks, we need a minimum set of information to be configured on our devices to be a member of that network. And there are a number of ways in which you can configure that information. So on that interface, we could manually configure information, and that would become static. Unless, of course, you went and changed it again. But that essentially would be static for some time. The bits of information that you need as a bare minimum to be a member of that network. You need an IP address at the network layer or layer 3, and you need a subnet mask. And it's the subnet mask that's logically ANDed, so you sort of do an AND function with any address to see which network that belongs to. So that will reveal the network address, or the network address of the LAN. And all devices connected to the same LAN must share the same network address. So those are two elements that we need, and they're your basic elements. And if you had other devices that were connected to here, you might have a printer connected to, or a print server. You'll probably have a network attachment storage device, or a media server, as it's probably its role. All of those devices would share the same network address, but they would have unique host addresses. So the final part of the address, if you like, will be unique. And that's absolutely true. That's got to be the case. Another thing that must be true as well is if we have a look at this LAN technology, the LAN technology that we're using in here is probably Ethernet. And as a result of that, we'll have an Ethernet address, and we all know and love those as our MAC addresses. So when you want to send an IP packet around the network, you have to create the IP packet and then pass it down to the Ethernet layer, which then frames that in an Ethernet frame and adds at least a source and destination address, together with a few other things, not least a checksum. And those addresses are 48-bit addresses, source and destination. And they again have to be unique. So they have to be unique within the network in which we're working. So your MAC address has to be unique, and within this space, within the LAN itself, or subnet, as we would call it in IP circles, we need an IP address reinforced by the mask, which would be unique again. Now, that's probably how we would set up IP addresses if we were involved in some form of testing, or we had a very simple network. And by that, I mean we'll be doing manual configuration. We can also do dynamic configuration or automatic configuration of IP addresses. And to do that, we'll need to add to this network a server function, and that server function could be a DHCP function. There's another one that you might be using, particularly in a corporate world, where you'll be using something called Radius. Radius is actually part of the AAA environment. That's our authentication, authorization, and accounting. But what we'll be using it for is not necessarily authentication, but to allocate network parameters such as the IP address of the actual devices. So we'll be using it in a very similar way to DHCP. DHCP is our dynamic host configuration protocol. And it does exactly what it says on the tin. It's the protocol which dynamically configures the hosts so that they can become a member of a given network. So they'll actually start off with an IP address which will actually be all zeros. So that is this computer as a definition. In other words, I haven't got an IP address, please give me an IP address. So that will trigger off something dynamic between your local devices and that DHCP server. So we'll see the starting point of that is that the local devices will send out a discover, because they probably don't have any information with regards to where those DHCP servers actually are, and they'll be using a broadcast address. So they'll be using an all ones address at the IP layer and at the MAC layer to get the information across to all stations on this network. And one of those stations on this network, of course, is the DHCP server. So the DHCP server is able to reply. Now, the first reply that comes back is actually an offer. Now, all of these messages are broadcast. So all stations get this information. The purpose of the offer is that there may be more than one DHCP server, and if there were, then you'd have more than one offer message. And then it's then up to the host to decide which of those offers that it wants to pursue. And it will do that by sending a DHCP request targeted against one of those DHCP servers. The reply or the accept message that comes back, that reply or accept, is the message that really now binds the user terminal to an IP address. And the information that we actually bind at this point is going to be an identity known to the host, and the identity that's known to the host, of course, is the MAC address. So we actually create a binding, and that binding will exist between the MAC address and the now new IP address, and this, of course, is the IP address that's been allocated by the DHCP server. So that's the automatic way in which we can configure things locally using DHCP in order to get an IP address at least, and together with that, of course, that has no real meaning unless you add the subnet mask to that. So that will also be included in the messages going back to the host. Now, that gets you, as far as we're concerned, access to the local network. But what if you want to go beyond that? What if you want to go beyond your local network and out towards the public internet? Well, the network that you're going to see is you're going to see the network that's provided by your ISP, and then there's an interconnect between the ISP and the big bad world of the internet, which will be using a BAS or BRAS, our broadband remote access server, or just simply broadband access server if it's the BAS. This beastie here that we see is in fact our SOHO router. Some people might see those as your hub devices, hubbing your services in and out of your premises. So what we'll see here is we'll see the LAN on the one side and we'll see access to the ISP on the other. Inside here, in the SOHO router, is where you're likely to find that DHCP function. So the DHCP function is actually another one of the elements in here. And that'll be allocating IP addresses to this locally connected LAN. Out here, we actually have another address. In fact, the address space is different. Inside our LAN, we'll use private addresses, and outside our LAN, we'll use public addresses. And the public address will come from the ISP space. So what they'll be doing is they'll be using their own DHCP or again radius functions in order to allocate IP addresses to these end terminals as well. And one of the other things that we haven't mentioned here is that the fact that the DHCP servers themselves may not actually be resident on the local LAN. And what you can find is that the LAN that you're dealing with may well have at the edge of its LAN is a DHCP relay, and again that might be in that edge router. And the job of that DHCP relay is to simply forward messages and then forward the replies to and from the DHCP server. So that's the only real addition. These are more or less transparent. They're just simply handling the messages here from the local hosts. So they're seeing the normal messages here and then just forwarding them on and then handling the replies coming back through to the end host. So it's really still a relationship between the host and the DHCP server that gets your IP address allocated automatically or as an auto config function. What about IPv6 then? And in fact, before I go to that, maybe it's worth considering some of the other things that you'll see, and this applies both here and in IPv6. Of course, we've talked about having an IP address, and we've talked about a subnet mask, and we've talked about bringing in a default gateway address so we can see the outside world. But that's great from an IP perspective. But of course, a lot of the time we actually work with names, and names need translating into numbers. So we have names, and we really want to put those into numbers, or vice versa for that matter. And this is where we'll bring in functions such as DNS. So we'll see this translation going on, mainly from names to numbers, but you can do reverse lookups, which take you back the other way. Names, of course, would include things like our website, which would be resolved to an IP address, which is then routable around the internet. So it'd be a good idea if DHCP could actually pass this information on as well. Another function that you'd like to see is something like network timing protocol. This is very important nowadays that we keep calendars and the like up to date. And this is an ideal way of making sure that all of your devices are synchronized if we know the address of a network timing protocol server. So we'll give you DNS server addresses and NTP server addresses, as well as part of the DHCP messages that are passed down to the end devices. That's not the only stuff that we can do in DHCP. It's been extended further. If you're doing voice over IP nowadays, then you'll probably be using SIP signaling, so session initiation protocol, and as you probably guessed it, we can also therefore give you the SIP servers addresses as well, as if your DHCP has been extended appropriately. So DHCP is a function. You can see it running on servers, you can see it running on routers. That's typically where you would see a DHCP function within any organization. And if you're in your Soho routers, then you're going to find that as a function normally resident on your default gateway, the way out. It'll be doing your local DNS, it'll be doing your local DHCP. What about IPv6? Slightly different world, IPv6. Of course, we've got a bigger address space to deal with, but also IPv6 started from a different standpoint. It saw some of the problems in IPv4 and improved upon them. So when we consider a device wanting to be a member of a network, what we have to bear in mind is that that physical interface there, if you remember, has an address already. It has an address when it's manufactured, and that address is its MAC address. Now that's a 48-bit address. What we do for IPv6 is we take that 48 bits and we increase it to 64 bits, and we create what's known as an EUI64. We take the two lots of 24 bits, split them apart, and insert in the middle 16 bits. We then flip the start of this. We actually we flip one of the bits in the first octet, and that then says we've got a well-formed EUI64, but it's tracked back from the MAC address. And if that's unique within your network, that's going to be unique within your network, and therefore it's a usable address. So what the local host does is it takes that what we know as the interface address, and it adds that to what's known as the link local prefix. And the link local prefix starts with FE80. And then we'll just add in that EUI64. And that should be unique then within that particular LAN. And to make sure it is unique, what the device will do is it will send out that link local address. It will sort of announce it to the other devices on this network, so that they could then determine if, hey, hang on a minute, I've got that address already. And if they have, they would reply back to say that they've got that address, and essentially the red flag, and you then have to manually configure that address on this local device. So what we're seeing here is we're seeing something of duplicate address detection. So we're determining whether or not that address exists elsewhere on this network. So it's link local. The scope is it's only here. And when we say link local, we're referring really to data link. And if you remember, Ethernet and MAC is at the data link layer. So the scope of this is as far, and it reaches only as far as this LAN. So only other devices connected to this LAN, which would of course include up to and including the interface here on a default gateway out. So that's just for local configuration, and that really gives you the ability to support plug and play. So IPv6 allows the devices such as your printers, and again, your network attachment storage devices to just switch on, and they should be able to see each other, and they announce themselves to everybody, so the other devices should be able to see those devices coming on board, and then they can interrogate further using other protocols to see what sort of things that they do and support. Once we got to this level, We can extend beyond that, because realistically what we want to do is we want to create something that's unique as a global unicast address, so we can now start to look at the rest of the internet and start communicating with it. So the next part of addressing is to effectively create a unicast address. So what we do is we listen out for prefixes for this network, and then we add on our tail, if you like, and we'll add on the bit that's going to be unique. Well, if this is already unique, why not add that again? So put the interface in here again. So we just need the prefix. We don't know what that is. That's the bit that you could say, well, that corresponds to the network address part that you saw in IPv4. Where did the prefix come from? Well, it actually comes usually from the locally connected routers. They have a set of prefix lists or prefixes, and they're associated with particular interfaces. So anybody requesting information on a given interface on a router would get a particular prefix back as a response. So what that does is, or what the router uses, is it uses router advertisements. And the router advertisements will include the prefix that's used for this network. So again, we'll create a unicast address, we'll check to see if it's unique, and then if so, we'll start to use it. So that's a classic way of performing address auto-config, really, because it's all done essentially under the hood. So all of this here is part and parcel of that, and it's really what we call stateless. So we're looking at address auto-config, otherwise known as Slack. So that gets you up and running, without much user intervention, which is pretty good, really, because if you remember, IPv6 addresses are 128 bits, and you've got to remember all of that in hex. So it'd be nice if it could be done under the hood. That's one method. There is another method, and again, it uses DHCP, but it's not DHCP as we know and love. It's very similar. It's DHCP v6. So again, probably here on our edge routers. So our default gateways out will actually be running DHCP, but it's v6. Now, DHCP v6 also has something called address delegation. And what you'll find is that out here there's another router acting as a delegating or delegation router for the purposes of DHCP. And what this does is it provides the prefixes for given networks. So this is centralized configuration of the prefixes. So we actually have identity association IDs associated with given prefixes. So if we make a request for a given ID, we should get back as a response the prefix associated with that. That then allows the edge router to then create an IPv6 pool, so that when we start to see DHCP requests coming in, we'll see then the responses going back out, which will be the IP addresses themselves. Slightly different model to before. We're not using broadcast messages now here. So when we see the local host communicating with that DHCP function, and it's DHCP v6 function, remember. First of all, we do a similar sort of thing that we saw before. And instead of using discover, we use the word solicit. So we're trying to find out if there's any DHCP servers out there, and that's using a well-known multicast address. So these all use multicast addresses. And then the response will go back in pretty much the same way as before. So we'll be advertising our presence. There may be multiple, and you'll choose one. Whichever one you choose, you can then request. And then you can get a subsequent reply coming back. So the response that comes back, and the response will include all that good DHCP stuff that we had before. So it's a very similar sort of model that we had before, but fundamental differences, we're now using multicasting. This is where we're actually getting IP addresses back, which is slightly different to the delegation function that we see going on here behind. There is also the capability to have DHCP v6 relays. of supporting then access to servers remote to that. And again, remember, this is a slightly different function in the sense that this is allocating the prefixes, not the whole address. The whole address is actually still assembled here by the DHCP server. So that's a couple of different ways that we've seen. We should also be mindful of what happens in the mobile world, particularly if you're working in LTE, and then you'll have the mobility management entity that's involved in communication. So we'll establish our initial connection. So we're doing attach. We'll be asked to establish an EPS bearer. So we can form a proper connection through here. But as part of this, there'll be a negotiation in terms of an IPv6 address. At the starting point, this isn't working over MAC. So what we get back from the MME isn't an IP address. What we get back from the MME is just the interface address, or the interface portion of the address. So that gives us a starting point, because otherwise we wouldn't know where we were. Because we've established a bearer, we've now got a bearer up into the network, which gets us up to our gateway routers. Specifically the PDN gateway device. And the PDN gateway device, of course, can now start the router advertisements. And those router advertisements will include, of course, the prefixes. So we get the interface in part of the bearer setup, and then we get the router advertisements in the sort of bog standard way, if you like, from IPv6. So a slight variant as far as mobiles are concerned, and certainly when you get all the way up to LTE. There's a couple of other variants. If you go back through history, I could go back through UMTS and GPRS, where we'll see signaling messages which will actually allocate you an IP address in a very similar way to DHCP. So very, very similar indeed. I suppose if we did go back in history a little ways, and we could also include it here, if you look at the mobile architecture over the radio access network, we would see in GPRS a GB interface, or an IUPS interface if you're talking about UMTS, of course, and that will then be terminated by an SGSN. In LTE we just change that to a serving gateway, and then we'll see an internal connection which connects us through to a GGSN, which is essentially the same place as our PDN gateway. These guys up here would be the ones that would be responsible for the sort of allocation of IP addresses, which they could do from an internal pool, or they could use DHCP, or they could use radius. So again, the same mechanisms as we pretty much talked about before. Well, that's some of the ways that we can do IP address allocation. You'll see there's plenty of other videos out there from Ray Castle with regards to some of the other aspects of IP. There's also a lot of information available at our website on www.raycastle.com. So look forward to seeing you on one of our future videos.